The surgeon said one word, and that word was not a diagnosis, not a prognosis, not a number or a timeline or any of the things you brace for when someone in scrubs walks toward you across a waiting room floor. The word was a material, a metal. And Daniel just stood there holding a paper cup of cold coffee, nodding like he understood, while his brain was still 3 floors up in the operating room with his wife. The surgeon moved on. Daniel sat back down in the plastic chair, set the cup on the floor, and stared at the ceiling for about 30 seconds. Then he pulled out his phone. He typed the word in, iridium. And then he sat there in that waiting room, in that specific smell of antiseptic and old carpet and recycled air, and read, and read, and kept reading. Because iridium belongs to a family of metals, a small, strange, almost secretive family. And the one that runs the whole operation, the one that the rest of the family orbits around, has a name that most people only ever associate with jewelry or old movies about wealth. Platinum. That was the word under every article he opened. Platinum this, platinum that. Platinum in the electrode keeping his wife's heart in rhythm. Platinum in the catalytic converter of the car he had driven to this hospital. Platinum in a drug being administered 2 floors above him to a man with cancer. Platinum in the definition of weight itself, stored in a vault somewhere in Europe that most people have never heard of. He sat in that waiting room for 4 more hours. By the time the nurse came to tell him everything had gone well, he had not thought about anything except this one metal and its completely insane journey through human history. This is that story. And I have to warn you, by the end of it, you will look at the world around you differently. Because the things holding it together are not the things you think they are. Let me start not with platinum itself, but with the question underneath it. How dependent are we, really, on things we cannot name? Not oil, not electricity, not water. Those ones we know. Those ones we talk about. I mean the quiet ones. The ones doing the actual structural work while we look elsewhere. Here is a number. Roughly 80% of all the platinum mined each year goes into 3 things: cars, food production, and medicine. That is not a coincidence. That is a picture of what civilization actually runs on. Remove platinum from the equation tonight, not just stop mining it, but erase every gram of it from every device and process it currently lives inside, and by tomorrow morning, the damage has already started. Every modern car built with a catalytic converter, which is essentially every car built in the last 50 years, begins running dirty. The chemistry that converts toxic exhaust gases into something a human lung can survive without long-term damage stops working. In cities where millions of cars move every single day, the air quality shift would not be subtle. You would feel it. You would taste it. People with respiratory conditions would feel it first, and they would feel it hard. But that is the part people can almost visualize. Here is the part they cannot. The industrial process that produces the nitrogen compounds used in synthetic fertilizers, the ones that allow modern agriculture to feed the current population of the planet, depends on a platinum and rhodium catalyst running at around 800 degrees inside chemical reactors. Without it, that process does not happen at the required scale. Agricultural scientists have estimated more than once in peer-reviewed work that synthetic nitrogen fertilizer currently supports the caloric needs of roughly half the people alive on Earth. Not supplements, not optimizers, supports. Remove the catalyst, and you eventually remove the food. Not next week, but the chain reaction starts tonight. And then there is medicine. Specifically, one family of drugs, all derived from a platinum compound, that are currently being administered to over 1 million cancer patients every single year. Not as an experimental treatment, as a standard protocol. For certain cancers, these drugs transformed survival rates so dramatically that the before and after numbers look like two different diseases. I will tell you exactly how that happened later, because the story of how platinum ended up inside cancer treatment is one of the strangest accidents in the history of science. It was not planned. It was not even looked for. A graduate student was running a completely different experiment, noticed something he probably should have ignored, and did not ignore it. That choice eventually saved millions of lives. But here is what stopped me cold when Daniel first told me all this, sitting across from me in his kitchen about 3 weeks after his wife came home from the hospital. He said, "Look, the thing that keeps getting me is not how important it is. It is how close we came to never knowing about it at all. Because for a long time, the people who found this metal did not want it. They literally threw it away." And that is where this story actually begins. Friends, if this is already pulling you in, hit subscribe and leave a like. It genuinely helps this channel keep going, and what comes next in this story is something I think you will want to hear. The first thing you need to understand about platinum is that it should not be here. Not on the surface of this planet, not in a river, not in your hands. The physics of how Earth formed should have made that completely impossible, and I will get to exactly why in a moment. But before the physics, there is a man. I will call him Marcus, because the name of the actual navigator who first documented this frustration has been softened by time and retelling into something almost mythological. Marcus is not mythological. He is tired and sweating, and he has been on a river in equatorial heat for weeks, and the gold is not coming as easily as the expedition's backers had promised it would. The river smells like wet clay and rotting vegetation. The air is so thick with humidity that breathing feels like a mild effort. Marcus is responsible for the sediment traps, the equipment used to catch dense particles washing downstream that might indicate gold deposits further up. And he keeps finding the same problem. Heavy grey stones, dull and slightly metallic, nothing like gold, nothing like silver, just wrong. They are dense enough that they throw off the whole washing process. They clog things. They add weight that should not be there. His job is to get rid of them. So he does. He picks them up one by one and drops them off the side into the water and watches them sink fast because they are extraordinarily dense for their size, and moves on. He is throwing away something that will one day be worth more per ounce than gold, more than the entire cargo of the ship anchored downstream. He is throwing it away because it is in the way. And that single image, a tired man dropping a fortune into a river out of irritation, is the image I keep coming back to when I think about how human beings relate to value. We are extraordinarily bad at recognizing it when it does not look the way we expected. Marcus was not stupid. He was not careless. He was working with the information and the frameworks he had. Gold looks like gold. This did not look like gold. Therefore, it was not worth keeping. That logic, applied to a substance born in the most violent event the universe produces, is almost poetic in its wrongness. Because to understand why what Marcus threw away was extraordinary, you have to go back further than any human history. You have to go back to before the sun existed. And that is not a figure of speech. The people who lived along those rivers before Marcus ever arrived had been working with that same grey metal for generations, and what they built with it would not be matched by European science for another 3,000 years. Let that sink in for a second. 3,000 years. While European alchemists were still arguing about what fire was made of, communities along those river systems had already solved a materials engineering problem that would stump the best chemists on the other continent for centuries after first contact. But I am getting ahead of myself. Let me stay with Marcus for one more moment, because there is something about his story that bothers me every time I think about it. He was not the first person to find those stones. He was just the first person in his particular cultural framework to find them and decide they had no value. The people who had been living in that region long before any expedition arrived had found the same stones in the same rivers and had done something completely different. They had paid attention. They had experimented. They had failed, tried again, failed differently, and eventually arrived at a technique that worked. Marcus picked up what they had figured out over generations and dropped it in the water in about 4 seconds. That gap between what those communities knew and what the arriving expeditions were willing to learn is one of the most expensive knowledge failures in human history. And nobody put it in the history books that way. Here is what those communities had actually figured out. The grey metal would not melt on its own. No fire they could build got hot enough. But they noticed something. When you mix the metal granules with gold and you heat that mixture, the gold melts first and flows between the granules of the harder metal, binding them together. Then you hammer that composite. Then you heat it again. Then you hammer it again. Repeat this enough times, across enough generations of trial and observation, and you end up with an alloy. Not pure platinum, not pure gold, something in between. Harder than either one alone. More resistant to wear. Better for tools, better for certain kinds of work, better for objects meant to last. They were not doing this by accident. They had developed a process, a repeatable, teachable, refinable process. That is not craft. That is engineering. And the arriving expeditions looked at it, decided it was primitive decoration, and moved on to find the gold. The reason this matters beyond the obvious historical injustice is that the technique those communities developed is essentially the same foundational concept that modern powder metallurgy is built on. The idea that you can take a metal in granular or powder form, combine it with heat and pressure, and produce a solid material with specific properties, that idea is the basis of manufacturing processes used today in aerospace components, in medical implants, in industrial cutting tools. The communities along those rivers arrived at the core logic of that concept through pure observation and repetition, without universities, without laboratories, without written records of prior experiments. They built the knowledge from scratch. And then Marcus threw their raw material into the river. What makes this particularly sharp is that the arriving expeditions were not uninterested in materials science in general. They were intensely interested in gold. They had an entire infrastructure built around finding it, testing it, transporting it, refining it. They had assayers and chemists and metallurgists on staff. They had equipment. They had institutional knowledge going back centuries. They just applied none of it to the grey stones, because the grey stones did not look like what they were looking for. And so one of the most significant materials on the planet got classified as waste by the people who had the tools to understand it, while the people who had already figured out how to use it were being pushed off their land. The irony is so complete, it almost feels constructed. But it was not constructed. It was just human. Now, here is the part that changes the whole picture. Those communities had worked with this metal because they found it useful. They had no idea what it was at a chemical level. Nobody did yet. But they had empirically discovered that it behaved differently from every other metal they knew, and they had built a working relationship with that difference over generations. The arriving expeditions, by contrast, had a theory about what valuable metals looked like, and anything that did not match the theory was discarded. One group was working from observation, the other was working from assumption, and the group working from assumption had all the ships and all the weapons and all the institutional backing. That is not a metaphor about platinum. That is a description of how knowledge actually gets lost, not through destruction alone, through the decision not to look. And the metal itself, sitting at the bottom of that river where Marcus dropped it, did not care about any of this. It was not waiting to be rescued or recognized or understood. It was just sitting there, dense and cold and unchanged, the way it had been sitting in riverbeds for millions of years before any human being ever walked past one. Patient is not even the right word for it. Patient implies waiting. Platinum does not wait. It simply does not change. And that quality, the refusal to react, the chemical stubbornness that made Marcus throw it away in frustration, is the exact same quality that would eventually make it the most sought-after industrial material on the planet. But before that could happen, it had to survive the European laboratory. And that is where things get genuinely strange. Every chemist who ever tried to melt platinum in a laboratory walked away feeling like the metal had personally insulted them, and I do not mean that loosely. I mean there are actual written records, letters and lab notes, where serious scientists describe this substance in language that sounds less like chemistry and more like a grudge. A chemist named Richard, working in a well-equipped European laboratory with access to the best furnaces of his era, received a small sample of the grey metal that had been making its way through scientific circles after arriving from South America. He had a reputation. He had solved problems that stumped his colleagues. He sat down with this sample fully expecting to crack it inside a week. He dropped it in acid first. Nothing. Not a bubble, not a color change, not a single visible reaction. The acid just sat there around it, looking embarrassed. He tried a stronger acid. Same result. He put the sample in his furnace, which could reach temperatures that would melt iron with room to spare. The platinum glowed. It went from grey to dull orange to a color that looked almost white at the edges. And then it just sat there, glowing, refusing to change state, radiating heat back at him like it was mildly annoyed by the whole situation. He pushed the furnace harder. The furnace complained first. The platinum did not. He wrote in his notes that evening, and I am paraphrasing because the original language was more formal, that the material appeared to exist in a separate relationship with heat than every other known substance, that it acknowledged fire without being governed by it. He tried for weeks. He got nowhere. What Richard was running into was not a limitation of his skill or his equipment. It was physics. Platinum melts at nearly 1,800 degrees. The furnaces available to chemists at that time, even the best ones, even pushed to their absolute limit, reached perhaps 1,400 degrees on a good day with optimal fuel and perfect conditions. That gap of nearly 400 degrees might as well have been a wall. And the thing is, platinum did not just refuse to melt. It refused to do almost anything. Most metals, when you heat them to extreme temperatures, start to oxidize, to react with the air around them, to form compounds on their surface. Platinum did not. It came out of the furnace looking exactly as it went in. No oxidation, no surface change, no evidence that anything had happened at all, except that it was hot. Richard reportedly held it with tongs after one session, set it on his workbench, and just stared at it for a while. That image feels very human to me. The best mind in the room, completely out of moves, just looking at the thing that beat him. This pattern repeated across multiple laboratories in multiple countries over several decades. Smart people, well-funded, well-equipped, systematically failing to do with platinum what they could do with any other metal they had ever encountered. And here is what I find genuinely fascinating about that period. The failure itself was scientifically productive. Because every chemist who failed to melt platinum learned something about what platinum was not. It was not reactive. It was not brittle. It did not degrade under extreme heat. It did not form compounds easily. Each failed experiment was accidentally building a profile of a substance with properties nobody had ever seen combined in a single material before. The metal was teaching them through resistance. They just did not realize yet how valuable those lessons were going to be. And then one of them found a workaround. Not a solution, a workaround. And that distinction mattered enormously, because the workaround was dangerous. The chemist who found it realized that if you introduced a third substance into the equation, something that would lower the overall melting threshold of the mixture, you could get platinum into a workable state without actually reaching its true melting point. The specific substance he used was toxic enough that the process had to be done near an open window, with the chemist periodically stepping back to breathe air that did not smell like a slow mistake. The result was a rough platinum mass, impure, inconsistent, but real, something you could actually shape. Word traveled fast through the scientific community, the way word always travels when someone cracks something that has been resisting everyone. But the method was messy, and it left contamination in the final material, and serious applications required something cleaner. That cleaner method was still years away, and the person who eventually found it would do something with the knowledge that nobody in that network of frustrated chemists would have predicted. But before we get to that person, we need to go somewhere else entirely. We need to leave the laboratories and the furnaces and the failed experiments and go somewhere much larger. Because while European chemists were arguing with platinum on the workbench, something was happening in the sky above all of them, above all of us, that put the entire struggle in a completely different context. Something that explains not just why platinum is hard to work with, but why it exists at all. And this is the part of the story where the scale changes so dramatically that it takes a moment to adjust. Here is what every physics teacher eventually tells their students about where the elements come from, and here is where that explanation quietly runs out of road. Stars make elements. That is true. A star is essentially a fusion reactor, pulling lighter atoms together to make heavier ones and releasing energy in the process. Hydrogen becomes helium, helium becomes carbon, carbon becomes oxygen. The process continues up the periodic table, and the star keeps burning, keeps fusing, keeps building heavier and heavier elements, until it hits iron, element 26. And then the star stops. Not because it runs out of material, because the math changes. Fusing elements lighter than iron releases energy, which is why the star burns. Fusing elements heavier than iron costs energy instead of releasing it. The star cannot sustain that. It collapses under its own gravity and explodes, scattering everything it built across space. Platinum is element 78. That number sits on the far side of a boundary that ordinary stars cannot cross. No main sequence star, no matter how massive, no matter how old, ever builds platinum through normal fusion. The physics simply does not allow it. So when you hold a piece of platinum, you are holding something that no star ever made the way stars normally make things. It required a completely different kind of event. An event so extreme that for a long time scientists could only theorize about it, because nothing in our observable neighborhood had ever been caught producing it in real time. Until one night, the detectors picked up something that changed everything. It started as a vibration, not a sound, not a flash of light, but a distortion in the fabric of space itself, so small that the instruments designed to catch it had to be isolated from every possible source of interference, from traffic on nearby roads, from the wind, from the footsteps of the technicians walking the corridors. The signal lasted less than 2 minutes, but in those 2 minutes, it carried more information about where platinum comes from than centuries of laboratory work had managed to produce. And what it described was not a birth, it was a collision. 2 dead stars, each one a collapsed stellar core the size of a small city but carrying the mass of an entire sun, had been slowly spiraling toward each other for longer than the Earth has existed. Think about that timeline for a second. While single-celled life was figuring out how to become multicellular life on this planet, while fish were learning to breathe air, while dinosaurs rose and vanished, while every chapter of human history was being written from first fire to first flight, those 2 objects were tracing their slow, inevitable spiral through space, getting incrementally closer with every orbit, bleeding energy away as gravitational waves, moving toward a collision that had been written into the physics of their situation from the moment they formed. And then they hit. The speed at the moment of contact was roughly 1/3 the speed of light. That number does not mean much until you try to hold it next to something real. The fastest spacecraft humanity has ever launched travels at about 60 kilometers per second. 1/3 the speed of light is about 100,000 kilometers per second. That is not a faster version of something familiar. That is a different category of event entirely. The collision lasted milliseconds. What it produced lasted much longer. An explosion so energetic that astronomers gave it its own classification, because the existing vocabulary for stellar explosions was not big enough. They called it a kilonova. The total energy released in those milliseconds exceeded what our Sun will produce across its entire 10 billion-year lifespan. But here is the part that connects back to everything we have been talking about. In the extreme conditions of that collision, temperatures and pressures so far beyond anything achievable in a laboratory that the numbers almost stop being useful, atomic nuclei began absorbing neutrons at a rate that nothing in normal stellar physics ever produces. Faster than they could decay. Faster than any stable process could generate them. And as each nucleus absorbed neutron after neutron, it climbed the periodic table. Past iron. Past the boundary that stops ordinary stars cold. All the way up to gold, to platinum, to iridium, to uranium. The heavy elements, the ones that have no business existing according to the physics of normal stellar fusion, were being assembled in real time in the debris cloud of two colliding neutron stars. When telescopes around the world turned toward the source of that gravitational wave signal, they caught the light from this event while it was still happening. And the spectrum of that light, the specific signature of which wavelengths were present and in what proportions, was the fingerprint of heavy element formation. Scientists could read it the way you read a label. Platinum was there. Gold was there. The amounts involved were staggering. The total mass of heavy elements produced in that single collision was several times the mass of the entire Earth. Not Earth's platinum, not Earth's gold, the entire Earth. That much new heavy element material, scattered across space in the aftermath of two dead stars finally meeting each other. And here is the connection that I think is genuinely hard to absorb, even when you understand the science. Every single atom of platinum that has ever existed on this planet was made in an event exactly like that one, or in one of its cousins. Billions of years before our Sun ignited, somewhere in the galaxy, one or more of these collisions happened. The debris spread across space. Some of it eventually became part of the cloud of gas and dust that gravity slowly pulled together into our solar system. The platinum that ended up in Earth was there from the beginning, baked into the raw material of the planet itself. The platinum in Daniel's wife's electrode. The platinum in the frustrated chemist's furnaces. The platinum Marcus threw into the river. All of it assembled in a millisecond collision between two city-sized objects moving at 1/3 the speed of light, billions of years before any human being existed to throw it anywhere. That is not poetry. That is the actual supply chain. And it creates a problem that the next part of this story is entirely about. Because platinum being present in the early Earth does not automatically mean it ended up anywhere we can reach. And this is where geology does something that feels almost deliberately cruel. When the young Earth was still largely molten, the heavy elements did exactly what physics told them to do. They sank. Platinum is one of the densest naturally occurring substances on the planet, 21 grams per cubic centimeter, which means a piece of platinum the size of a golf ball weighs about as much as a large apple, which does not sound dramatic until you hold one and feel your wrist drop with a weight your eyes did not prepare you for. In a molten planet, that density is a one-way ticket downward. Iron sank to form the core. Nickel followed. Platinum went with them, pulled toward the center by the same gravity that was pulling everything else, settling into the deep interior of a planet that was busy assembling itself. The calculations that geochemists have run on this process suggest that the Earth's core contains roughly 1,000 times more platinum than the entire crust. 1,000 times. It is sitting down there, about 3,000 kilometers below the surface, completely unreachable, locked inside a ball of iron and nickel at temperatures and pressures that make platinum's melting point look trivial. All that cosmic material, all those atoms forged in a stellar catastrophe, and almost all of it, ended up somewhere we can never get to. The platinum we mine, the platinum in every industrial process and medical device and jewelry case in the world, that is not the original batch. That came later. And the way it arrived is one of those geological facts that sounds made up until you look at the evidence. After the Earth had cooled enough to form a solid crust, after the surface had hardened into something resembling a planet rather than a lava ocean, something started hitting it. A period that geologists call the Late Heavy Bombardment, a sustained assault of space rocks lasting millions of years, delivered a fresh wave of material from the outer solar system onto the surface of the young Earth. These were not gentle arrivals. These were objects large enough to leave impact craters that have long since been erased by geological time. And they brought platinum with them. This new delivery landed on solid ground instead of molten rock. It did not have time to sink to the core before the crust locked it in place. It stayed near the surface, distributed through the upper layers of the planet, gradually concentrated by geological processes over the following billions of years into the deposits that eventually became mines. The platinum Marcus threw into that river had arrived on Earth as cargo inside a rock falling from space after being forged in a stellar collision that predated the Sun. It had survived a meteorite impact, billions of years of geological pressure and gradual erosion into a riverbed, and then a tired navigator decided it was in the way and dropped it in the water. That sequence of events is so improbable that if you wrote it as fiction, an editor would ask you to make it more believable. But it is exactly what happened. And the story of what platinum did next, once it finally got into the hands of people who were willing to take it seriously, is where things get genuinely complicated. The man who finally cracked platinum did not publish his method for over 20 years, and the reason why is one of the most unsettling decisions in the history of science. But before we get to Edward and his very deliberate silence, we need to pick up where we left off, because the story of how platinum moved from riverbed curiosity to serious scientific obsession runs directly through a laboratory that smelled like sulfur and burnt coal, and the particular kind of frustration that only happens when an intelligent person keeps failing at the same problem. Richard had given up. Not publicly, not officially, but in the way that matters, which is that he stopped trying new approaches and started writing careful descriptions of all the approaches that had failed. That documentation, ironically, was enormously useful to the people who came after him, because when the next generation of chemists picked up platinum samples, they already had a map of dead ends. They did not have to rediscover that acid did nothing. They did not have to rebuild every failed furnace experiment from scratch. Richard's meticulous record of failure was, in a strange way, the most productive thing he contributed to the platinum problem. The knowledge of what does not work is still knowledge. The chemist who made the first real breakthrough was working in a city far from the centers of scientific prestige, in a modest laboratory with equipment that was good but not exceptional. And he arrived at his method not through a flash of inspiration, but through the same slow, grinding process that the river communities had used centuries earlier. Trial, failure, adjustment, repeat. What he discovered was that if you dissolved platinum in a specific acid mixture, then introduced a particular compound into the solution, You could cause the platinum to fall out of the liquid as a fine powder, a precipitate. Grey, almost silky in texture, so fine it would coat your fingers if you touched it dry and leave a metallic smear that took several washes to fully remove. That powder could then be pressed under significant mechanical force into a solid shape, and when heated, not to platinum's full melting point, but to a much lower temperature, the particles would fuse together just enough to hold their form. The result was not perfect. It was porous at a microscopic level, slightly brittle compared to what fully melted and cast platinum would theoretically produce, and the properties varied depending on exactly how finely the powder had been ground and how much pressure had been applied during forming. But it worked. You could shape it. You could machine it. You could produce objects from it with consistent enough properties to be genuinely useful. And when word of this method reached the right ears, the reaction was not purely scientific excitement. It was something more complicated than that, and it happened fast. Because someone in a position of authority immediately understood something that the chemist himself had not fully worked through. Platinum was denser than gold, significantly denser. Gold sits at around 19 grams per cubic centimeter. Platinum sits at over 21. That difference means that a platinum object of a given size will weigh noticeably more than the same object made from gold, which means that if you wanted to create a gold object that weighed exactly the right amount on a scale, you could make it from a platinum core covered in a thin layer of gold and use a slightly smaller total volume and hit the target weight precisely. A standard test for gold at that time involved checking the surface of the metal and checking the weight. A platinum core with gold plating would pass both. The implications for anyone dealing in gold bars, gold coins, or any commodity priced by weight and purity were severe. This was not a theoretical concern. This was a blueprint for a scheme that could silently drain value from every gold transaction in a trading economy, and it would be nearly impossible to detect without cutting the object open. The method was classified almost immediately, access was restricted, and the chemist who found it was well compensated and firmly encouraged not to discuss it outside approved channels. The knowledge existed. It was real, it was workable, and it was locked away. But knowledge has a way of not staying locked. It seeps. It travels in letters between scientists who trust each other. It surfaces in conversations at the edges of official meetings. And within a generation, a man named Edward had not only independently arrived at a cleaner version of the same method, but had also thought through the financial danger more carefully than anyone before him. Edward understood chemistry. But he also understood what would happen to the trading systems his entire world depended on if this process became widely available. And his solution to that problem was both elegant and deeply self-interested, which is often how the most consequential decisions get made. He said nothing. He published nothing. He simply began producing very high-quality platinum labware and selling it quietly through a network of intermediaries, with no explanation of how it was made, at prices that reflected the difficulty of the process without revealing what the process actually was. For over 2 decades, he ran what was effectively a monopoly on workable platinum, hidden inside the ordinary commerce of laboratory supply. His colleagues knew he had solved something. They did not know what. He deflected questions with the practiced ease of someone who had rehearsed the deflection many times. He was charming about it. He was frustrating about it. And he was getting steadily wealthier from it, which some of his colleagues found difficult to separate from the question of whether his silence was principled or purely mercenary. The answer, as far as anyone can tell from the letters and records he left behind, was both. He genuinely believed that releasing the counterfeiting potential of the method into open scientific literature was dangerous. He also genuinely enjoyed being the only person who knew how to make something that everyone else wanted. Those two motivations do not cancel each other out. They coexisted, the way most real human motivations do, in a space that is too complicated for a simple verdict. But here is what Edward could not have anticipated. While he was quietly selling his labware and keeping his secret, a completely different group of people had found a completely different use for platinum, one that had nothing to do with counterfeiting or chemistry or any of the problems he was managing. They needed it because they were trying to define reality itself. And they needed it to last forever. Imagine finding out that the entire financial system of your era could be quietly dismantled using a method only you knew, and then choosing to sit on that knowledge for over 2 decades while getting rich from it. That is exactly what Edward did. And the more I think about it, the more I find myself unable to decide whether that makes him a villain or the most responsible person in this entire story. Maybe both. Maybe the line between those two things is thinner than we like to think. While Edward was running his quiet monopoly, selling pristine platinum crucibles and vessels through intermediaries who asked no questions and received no explanations, the confirmed cases of gold fraud using platinum cores were already appearing in trading centers across Europe. Jewelers were cutting open suspect bars and finding the wrong metal inside. The weight had been right. The surface had passed every standard test. But the interior was platinum, dense enough to match the target mass at a smaller volume, covered in gold plating thick enough to fool a surface scratch. Edward knew about these cases. He followed them carefully. Each one confirmed what he had calculated years earlier. The method was out. Not his specific version, not his clean, reliable process, but the underlying principle had leaked into enough hands that the fraud was happening anyway. What he had prevented by staying silent was not the concept, it was the scale. His version was efficient enough and consistent enough that if published, it would have made the fraud trivially easy for anyone with a basic laboratory. The crude versions floating around were detectable if you looked carefully. His would not have been. He began releasing fragments of his method in the final years of his life. Not all at once, not as a formal publication, but in conversations with specific colleagues he trusted, in careful letters that disclosed pieces of the process without assembling the complete picture in any single document. It was a controlled dissolution of a secret he had held for so long that keeping it had become a habit. When he died, he left a significant portion of his accumulated wealth to a scientific institution, enough to fund prizes and fellowships for generations. The medal that institution eventually named after him became one of the most respected awards in his field. His public reputation was that of a brilliant and generous scientist. The full picture of how he had built that wealth was something only a few people understood completely, and they were not inclined to publicize it. That is how Edward became a celebrated figure in the history of science, rather than a complicated footnote in the history of financial crime. The distinction between those two outcomes was mostly a matter of whose version of the story got written down first. But here is where the story takes a turn that Edward could never have engineered, because it happened in a completely different world from the one he operated in. While he was managing his secret in private laboratories and gentlemen's correspondence, a government commission in a country going through the most radical political transformation of its era was trying to solve a problem that had nothing to do with chemistry and everything to do with trust. The problem was measurement. Specifically, the fact that measurement was a disaster. The system that existed before this commission went to work was not really a system at all. It was a collection of local habits that had calcified into official units over centuries. The distance, called a foot, was different depending on which city you were standing in. The weight, called a pound, varied by region, by trade, by the type of goods being weighed. A merchant moving goods from one province to another needed to mentally convert between different units at every stage of the journey, and the opportunities for honest error and dishonest manipulation were everywhere. This was not a minor inconvenience. It was a structural problem embedded in every commercial transaction, every legal contract, every engineering project across the entire country. The Commission's mandate was to replace all of it with something rational. Something based not on tradition or the arbitrary decision of some long-dead local authority, but on nature itself, on constants that would be the same everywhere, for everyone, forever. The meter was defined through the geometry of the planet. The kilogram was defined through the behavior of water at a specific temperature. The logic was beautiful. If you lost every physical standard and needed to reconstruct the system from scratch, you could do it. You would just need to remeasure the Earth and the density of water. The definitions were anchored to reality, not to objects. But definitions still needed physical embodiment. You needed something you could hand to a tradesman or a scientist or a judge and say, "This is the standard. Measure against this." And the moment you decided to make physical standards, you had to choose a material. And the choice was not straightforward, because whatever material you picked had to do something that no material does naturally. It had to remain unchanged for an indefinite period of time, under real-world conditions, handled by real people in real institutions across generations. The Commission considered their options methodically. Wood changes with humidity. Iron corrodes. Silver tarnishes. Glass is too brittle. Copper oxidizes slowly but measurably. Gold was a candidate, softer than ideal but chemically stable. Then someone put a piece of platinum on the table. The same metal that had defeated every furnace in Europe, the same metal that sat in acid without reacting, the same metal that came out of extreme heat, looking exactly as it went in. The same metal that Edward had been quietly turning into laboratory vessels precisely because it did not interact with anything it touched. In the context of a room full of people trying to find a material that would not change, the choice became obvious quickly. Not unanimous immediately, but obvious. Platinum was the only substance they had encountered that seemed to treat the passage of time as genuinely irrelevant to its condition. And so they chose it. And what they built from it would sit at the center of the world's measurement system for longer than any of them could have imagined. Until it developed a problem so philosophically strange that it took a completely different branch of science to resolve it. For over a century, the official definition of 1 kilogram was a small metal cylinder sitting in a basement, and the terrifying part is that nobody could prove it was not slowly changing. Let me explain exactly why that is so much more unsettling than it sounds. The commission that chose platinum had done their job well. They specified a precise alloy, 90% platinum and 10% iridium, because pure platinum is soft enough to scratch with a fingernail and iridium adds hardness without compromising the chemical stability. The cylinder they produced was machined to exact dimensions, polished to a mirror finish, and locked inside a climate-controlled environment protected by 3 nested glass bell jars and a vault requiring 3 separate keys held by 3 separate officials. No single person could access it alone. The whole arrangement was designed to communicate through sheer institutional weight that this object was beyond ordinary handling, beyond ordinary risk, beyond ordinary change. And for the first few decades, it worked beautifully. Countries that signed the international agreement received their own official copies, precise replicas of the original, and the global system of weights ran smoothly on the shared understanding that all these cylinders were consistent with each other and with the one in the vault. Then the comparison sessions started. Every few decades, the official copies were brought back and measured against the original, and the numbers were not quite right. Some copies had gained a few tens of micrograms. Some had lost a similar amount. The differences were invisible to any scale used in ordinary life. You would never notice them weighing fruit at a market or measuring ingredients in a kitchen, but in precision science, in pharmaceutical manufacturing, in materials research, in any field where measurement accuracy propagates through a chain of calculations, those microscopic drifts mattered. They accumulated. They introduced uncertainty into processes that could not afford uncertainty. The obvious response was to figure out which objects had changed and recalibrate accordingly. But here is where the logic collapsed completely. The original cylinder was the definition of 1 kilogram, not a representation of it, not an approximation of it, the definition. By the rules of the entire system, whatever the original weighed at any given moment was exactly 1 kilogram, because that is what 1 kilogram meant. If the copies had drifted away from the original, the copies were wrong by definition. End of discussion. But if the original had drifted, and the copies had stayed stable, you still could not say the original was wrong, because the original was incapable of being wrong by definition. It was the ruler you used to measure all other rulers, including itself. There was no external reference. There was no higher authority to appeal to. The standard was simultaneously the question and the only permitted answer, and that circularity was baked into the foundation of the whole system. Scientists working in precision measurement had been quietly uncomfortable with this for years, not loudly, not in ways that created public alarm, because the practical impact on everyday life was genuinely negligible. But in the specific corridors where people thought hard about what measurement actually means and what it requires to be reliable across time and across different places in the universe, the platinum cylinder was a problem wearing a very convincing disguise as a solution. The disguise held for over 100 years. Then quantum physics handed metrology, which is the science of measurement, a way out that nobody in the commission that made the original cylinder could possibly have anticipated. The solution came from a number. Not a physical object, not a material, a number. A fundamental constant of nature that describes the relationship between the energy carried by a single packet of light and the frequency of that light. This constant appears in the equations that govern how atoms absorb and emit energy. It appears in the equations that describe how semiconductors work, which means it is embedded in every electronic device ever made. It is one of the fixed features of the universe, as far as physics can determine, the same in every location, the same at every point in time, unaffected by temperature or pressure or the handling practices of institutional custodians. Scientists had been measuring this constant with increasing precision for decades, using an instrument called a Watt balance, which compares mechanical power to electrical power through a chain of measurements anchored in quantum effects. By the time the decision was made to redefine the kilogram, this constant was known to 9 decimal places. The kilogram was redefined through it. 1 kilogram became the mass that, when used to calculate a specific quantity of energy through that constant and the speed of light, produces a precise numerical result that is fixed forever. What that means in practice is that any sufficiently equipped laboratory anywhere in the world can now realize a kilogram from scratch using quantum measurements without reference to any physical object. The kilogram exists in the laws of physics now, not in a vault. It is the same on every continent. Theoretically, it would be the same on Mars. The platinum cylinder in its temperature-controlled room, behind its 3 glass bells, under its 3 keys, is no longer the kilogram. It is a very precise antique. A monument to a system that worked better than anything before it, and not quite well enough for what came after. But here is what stays with me about that cylinder. When technicians opened the vault after the redefinition to conduct what was essentially a final formal inspection, the cylinder looked exactly as it had when it was first placed there. The polished surface showed no tarnish. The edges showed no visible wear. The material had not reacted with the air around it, despite over a century of exposure inside the bell jars. The world that surrounded it during those 100+ years had changed beyond recognition. The governments of the countries that originally built the system no longer existed in their original forms. 2 large-scale wars had reshaped entire continents. The technology in the room monitoring the vault's climate would have looked like magic to the people who first locked the cylinder away. And the cylinder just sat there, reflecting light off its polished surface, unchanged, unbothered, completely indifferent to everything that had happened around it. That image kept coming back to Daniel when he thought about all of this later. He told me that what struck him was not the science, it was the stubbornness, the sheer refusal of this material to participate in the decay that everything else around it was going through. And that quality, that same chemical indifference that made Marcus throw it away, that made furnaces fail, that made Edward rich, that made it the only reasonable choice for the world's measurement standard, that same quality was about to show up somewhere nobody expected it. Not in a vault, not in a laboratory, inside a human body. And the way it got there is the strangest accident in this entire story. Daniel was not a chemist. He was a biophysics graduate student who spent most of his working hours in a lab that smelled like saline solution and warm electronics, staring at data that moved slowly and meant things only about a dozen people in his field fully understood. He was not looking for anything dramatic. He was not on the edge of a breakthrough. He was doing the unglamorous middle portion of a long research project, running the same experiment in slightly varied conditions, checking whether electric fields applied to living cells at specific frequencies had any measurable effect on how those cells divided and grew. It was careful work. It was important work. It was also, on most days, extremely boring work. And then one morning, he walked in, looked at his cultures, and felt the specific cold feeling that comes when the data is telling you something your experimental design cannot explain. The cells had stopped dividing. Not slowed down, stopped. The cultures that had been running overnight under the electric field showed almost no new division activity compared to the control group. Daniel checked the temperature first, because temperature is the most common culprit when cell behavior goes strange. Normal. He checked the nutrient medium, the liquid the cells were growing in. Normal. He checked the equipment settings, the frequency and amplitude of the field, the timing cycles. Everything was exactly where he had set it. He stood in the lab for a long moment, looking at the cultures through the microscope, watching cells that should have been dividing just sitting there, and ran through the list of possible explanations methodically. Contamination was the most likely answer. Something had gotten into the medium and stressed the cells enough to halt their division cycle. He would need to start the cultures fresh, sterilize everything and run it again. But before he scrapped the batch, something made him pause. The cells were not stressed in the way contamination usually produced. They were not dying. They were not clumping. They were not showing the irregular shapes that chemical stress typically caused. They looked, under the microscope, essentially healthy. Just stopped. As if someone had found a pause button for a specific biological process and pressed it without disturbing anything else. That specific quality of the anomaly was strange enough that Daniel decided not to discard the cultures immediately. He decided to spend one more day looking at them first. That decision, made in about 30 seconds by a tired graduate student who almost certainly would rather have gone to get coffee, turned out to matter more than most deliberate choices made in that field for the next several decades. He started eliminating variables one by one with the systematic patience that good experimental science requires, and that looks, from the outside, almost indistinguishable from stubbornness. He swapped out the culture dishes. Same result. He replaced the nutrient medium entirely. Same result. He changed the electrode placement. Same result. He ran the experiment without the electric field at all. Just the cells and the medium and the electrodes sitting in it without any current applied. And the cells still did not divide normally. That was the moment the contamination explanation stopped working. Because if the cells behaved abnormally even without the field was not the variable causing the effect. Something else was. And the only things that had been in contact with the medium throughout every version of the experiment were the electrodes themselves. The electrodes were platinum. Daniel had chosen them for exactly the reason every researcher chooses platinum electrodes for biological work. Platinum is inert. It does not react. It does not leach compounds into the surrounding medium. It sits in the solution and conducts electricity and does nothing else, which is precisely what you want when you are trying to isolate the effect of electricity alone on a biological system. Platinum was his control. It was the thing that was supposed to not be a variable. And now it was the only remaining explanation. Something from the platinum electrodes was getting into the medium and stopping cell division, which should have been chemically impossible, and which he could therefore not report to anyone until he had figured out what it actually was. What he eventually found, after weeks of careful chemical analysis of the medium, was a platinum compound. A molecule containing a central platinum atom bonded to 2 chlorine atoms and 2 ammonia groups in a specific geometric arrangement. This compound formed when the electrodes, under the influence of the electric current in a chloride-containing solution, released platinum atoms that then combined with the available molecules in the medium. It was not a large amount. The concentration was tiny. But it was enough. And the geometry of that molecule turned out to be everything. there is a companion molecule with an almost identical chemical formula. Same atoms, same types of bonds, just arranged differently in space. One version has both chlorine groups on the same side of the central platinum atom. The other has them on opposite sides. These two arrangements behave completely differently in a biological environment. The version that forms under the conditions of Daniel's experiment, with the chlorines on the same side, is the one that stops cell division. The other version does essentially nothing. The difference between a molecule that halts cell growth and one that does not is the three-dimensional position of two atoms. That is the margin. That is how specific the chemistry is. When Daniel understood what he had found, he did not immediately think about medicine. He was a biophysicist. He thought about the mechanism. He thought about why a platinum compound in low concentration would selectively interfere with cell division while leaving the cells otherwise apparently functional. He wanted to understand the biology before he started speculating about applications. But his supervisor, when Daniel finally brought the data to him, made the connection faster. Because his supervisor had a background that touched the edges of cell biology and oncology, and he recognized immediately what a compound that specifically halted cell division without killing cells outright might mean for the treatment of cancers, which are defined by exactly that process going wrong. Cells that divide without stopping. Cells that ignore every normal signal to pause. If you had something that could impose that pause, regardless of what the cell's internal signals were saying, you had something worth pursuing with urgency. The two of them looked at each other across the lab bench in a moment that neither of them described publicly for years afterward, because neither of them wanted to overstate what they had before they had tested it properly. The first animal studies produced results that made it very hard to stay calm. Tumors that had been growing steadily in the test subjects slowed. Some stopped entirely. The compound was reaching the rapidly dividing cells, getting inside them, and doing something to their DNA that shut down the copying process. The cells could not replicate a genome they could not read. They could not divide without replicating their genome. They triggered their own internal shutdown sequence. And because tumor cells divide far more frequently than most normal cells, they encountered the compound far more often, making them significantly more vulnerable than the surrounding healthy tissue. The selectivity was not perfect. Normal cells that divided quickly were also affected, which explained the side effects that would later be documented in human patients. But the therapeutic window, the gap between the dose that damages tumors and the dose that becomes dangerous to the patient overall, was real and workable. The compound moved into clinical trials. The results in certain cancer types were not incremental improvements on existing treatments. They were transformations. For one specific form of cancer in particular, the survival rate went from a number that barely qualified as hope to a number that qualified as a genuine cure in the majority of cases. A disease that had been a near certain outcome became, with platinum-based treatment, something most patients survived. That shift happened within a single generation of oncology. And it started because a graduate student chose not to throw away an anomaly that most people would have dismissed before finishing their morning coffee. The entire global push toward hydrogen energy is about to run into a wall that almost nobody is talking about publicly, and that wall has a name, and that name is platinum. Let me explain what is actually happening, because the version of this story that makes the news is about clean fuel and zero emissions and the future of transportation. All of that is real, But underneath it is a supply problem that the engineers working on these systems think about constantly and that most people have never heard mentioned once. Hydrogen fuel cells are not a concept anymore. They are in production vehicles driving on real roads in multiple countries right now. They are in regional trains that replaced diesel locomotives on specific routes. The technology works, the chemistry is solid, and the chemistry requires platinum. The way a hydrogen fuel cell generates electricity is through two simultaneous chemical reactions happening at two separate electrodes. Hydrogen comes in on one side, oxygen on the other. The hydrogen gives up its electrons at one electrode, those electrons flow through a circuit producing usable electricity, and on the other side, they reunite with oxygen and hydrogen ions to produce water. The exhaust is water vapor. That is the entire output. No carbon, no particulates, no combustion byproducts of any kind. The reason this matters for platinum is that both of those electrode reactions need a catalyst to proceed fast enough at the operating temperatures of the cell to be practically useful. Without a catalyst, the reactions still happen, but too slowly to power anything. With the wrong catalyst, the system degrades quickly under real operating conditions. The best catalyst science has found for this application, tested across decades of research and real-world deployment, is platinum. Nothing else currently available combines the activity, the durability, and the stability that these systems need across hundreds of thousands of hours of operation. A hydrogen fuel cell vehicle today uses significantly more platinum than a conventional catalytic converter. We are talking roughly 3 to 4 times more per vehicle. Now consider that the total annual platinum mining output for the entire planet sits at somewhere around 180 to 200 tons. Consider that global vehicle production runs at roughly 80 to 90 million units per year. The arithmetic does not work. If even a fraction of global vehicle production shifted to hydrogen fuel cells at current platinum loading rates, demand would outstrip supply by a margin that no increase in mining could realistically close. The deposits are where they are. The Bushveld complex in southern Africa holds the majority of accessible platinum reserves on Earth, concentrated in seams sometimes less than a meter thick at depths of over 2 kilometers, requiring months of processing per ounce of final metal. You cannot simply decide to mine more and have the supply appear. The geology is what it is. Researchers working on this problem are moving on several tracks simultaneously. One track is reducing the amount of platinum needed per cell by applying it in layers only a few nanometers thick using precision deposition techniques, getting more catalytic surface area from less material. Progress on this has been real and substantial over the past 2 decades, but there is a physical limit to how thin you can go before the catalyst loses effectiveness. Another track is finding substitute materials entirely, and this is where significant scientific effort is concentrated right now. Iron-based compounds on carbon supports have shown genuine promise in laboratory settings. Certain alloys of nickel and cobalt have demonstrated catalytic activity in controlled conditions, but none of them, as of right now, perform comparably to platinum under the full range of conditions a real fuel cell experiences over years of actual use. The gap between laboratory promise and real-world durability is wide, and crossing it has taken longer than optimists projected. The third track is recycling, recovering platinum from end-of-life fuel cells and catalytic converters and returning it to production. This already happens at significant scale for automotive catalysts, with roughly 30% of market supply coming from secondary sources. But recycling cannot create new supply from nothing. It can only slow the rate at which the gap between demand and availability grows. And so the conversation that began in science fiction has moved into engineering departments, into investment analyses, into the strategic planning documents of companies that build the infrastructure of the energy transition. The asteroids. Specifically, the class of space rocks that geologists call chondrites, primitive bodies that never went through the kind of planetary differentiation that sent Earth's platinum to an unreachable core. These objects retained their original composition from the early solar system, the same proportions of elements that existed in the cloud of material that formed everything in our neighborhood of the galaxy. Their platinum group metal concentrations are, by Earth crustal standards, extraordinarily high. Not uniformly, not in every asteroid, but in enough of them that the numbers attract serious attention from people who think carefully about resource economics over multi-decade timescales. A probe is already traveling toward one of the largest metallic objects in the asteroid belt, gathering data that will directly inform the feasibility calculations for eventual extraction. The mission is described as scientific, which it is. It is also, unmistakably, a prospecting expedition. The science and the commerce are not separate here. They are the same question asked with different vocabulary. The economic logic is straightforward even if the engineering is not. If hydrogen energy scales to the point where it represents a meaningful fraction of global power generation and transportation, and the policy directions of major industrial economies strongly suggest that is the intended trajectory, then platinum demand at current technological levels exceeds what Earth can supply. When a gap between demand and available supply becomes large enough and persistent enough, the cost of solving it through unconventional means starts to look reasonable by comparison. The cost of launching extraction infrastructure to near-Earth asteroids is enormous by any current standard. But enormous compared to what exactly? Compared to leaving an entire energy transition stalled for lack of catalyst material, the arithmetic eventually flips. Not next year, not in 10 years, but the engineers running these projections are not thinking in 10-year windows. They are thinking in the timescales that energy infrastructure actually operates on. And in those timescales, the metal that Marcus threw into a river, the metal that defeated European furnaces for generations, the metal that accidentally became a cancer treatment, the metal that defined the kilogram, is pointing humanity toward its next genuinely necessary frontier. Not because of romance, because of need. Now we come back to Daniel. Not to the waiting room at the beginning, but to his kitchen 3 weeks after his wife came home. He told me this story across a table with 2 cups of coffee going cold between us, and I remember the specific way the late afternoon light was coming through the window behind him, laying a long rectangle of gold across the kitchen floor, and how strange it felt to be sitting in that ordinary domestic light, talking about neutron stars and river navigators and cancer wards and asteroid probes. His wife was upstairs, recovered, doing something normal, and the iridium electrode that had kept her heart in rhythm during surgery was still inside her, doing its job without her thinking about it. He said, and I'm going to try to get this right because he said it simply and it landed hard. He said that what got him was not any single piece of the story. It was the chain. The way each thing connected to the next without any of the people involved intending the connection. Nobody who witnessed that neutron star collision, if anyone had been there to witness it, was thinking about cancer patients. Nobody in that river colony was developing a supply chain for the Industrial Revolution. The communities who figured out how to work with the grey stones were not contributing to a measurement system they would never hear of. Richard, the frustrated chemist, was not paving the way for a biophysics experiment centuries later. Edward, counting his monopoly profits, was not funding the eventual discovery of a kilogram standard. And Daniel himself, staring at cells that would not divide, was not thinking about his wife's future surgery. The chain assembled itself. Every link was added by someone who could only see one or two links in either direction. The full length of it was invisible to everyone who built it. What that means, I think, and this is the thought I have been sitting with since Daniel told me this, is that the things we build by paying attention outlast us in ways we cannot predict and cannot own. Marcus paid no attention and lost the chain. The river communities paid close attention and added a link that survived them by millennia. Richard paid attention to his failures and documented them carefully enough that the people who came after him did not have to repeat them. Daniel paid attention to an anomaly that was easier to ignore, and that attention eventually sat inside his wife's chest, keeping her heart in rhythm. The metal itself paid attention to nothing, because metal does not pay attention. It just held its structure across billions of years of cosmic violence and planetary formation and human history, unchanged by any of it, available to whoever was paying close enough attention to see what it actually was instead of what they expected it to be. That is not a lesson about platinum. That is a lesson about the only thing that actually moves human knowledge forward. Not genius, not resources, not ambition. Attention. The willingness to look at what is actually in front of you and resist the temptation to see only what you came looking for. Marcus saw waste and threw it in the river. Daniel saw an anomaly and followed it into a discovery that changed medicine. The difference between those two outcomes is not intelligence. It is the choice to keep looking when looking is inconvenient. Here is the question I want to leave you with, and I genuinely want to know what you think. Right now, today, in your own life, in your own field, in whatever work or curiosity occupies your time, what is the thing you keep setting aside because it does not look like what you came looking for? What is your grey stone in the river? Because if this story means anything, it means that the most important things rarely announce themselves. They sit in the sediment trap looking like interference, waiting for someone patient enough to wonder why they are there. Write it in the comments. I am not being rhetorical. I actually want to read them. And if this story made you think, if it shifted something even slightly in how you see the ordinary objects around you, hit the like button and subscribe. There are more stories like this one, stories about the invisible architecture of the world we live in, and every like and subscription makes it possible to keep telling them. Thank you for listening all the way to the end. That is not nothing.